atoms in the third or higher periods, which have access to d orbitals, they've got more orbitals, the energy levels are closer together, they can have more than 8 valence electrons. This is called an expanded octet. You can even have more than 4 bonds, believe it or not. So let's dig in. Let's look at sulfur tetrafluoride. So for sulfur tetrafluoride, let's start out. You've got S in the middle. You've got 4 fluorines, and the total number of valence electrons. And now with these expanded octet ones, we start adding up lots of valence electrons. 6 plus 4 times 7. So that's going to be 6 plus 28, 34 electrons. And we've got 8 in bonds. So we've got 26 electrons we need to place. Okay, that's 26 divided by 2 equals 13 lone pairs. We know that fluorines are electronegative. They love lone pairs. So let's give a full octet to each of the fluorines. And we've placed 12 lone pairs. We got one more lone pair to go. Well, where's it going to go? Fluorine is up on the up near the top of the periodic table. It's not going to do it, but sulfur is lower. It has access to the d orbital, so it can actually hold more electrons. So what we find is that the one that's most consistent with the rules we have so far and with experiment is putting that lone pair on sulfur. So that would be the Lewis structure of sulfur tetrafluoride. The electrons have to go somewhere. The most logical place for them, the most stable place for them to go is on top of the sulfur. And now it has 10 electrons around the central atom instead of 8. That is an example of an expanded octet. Let's dig in more. Okay, so this is a nice example. I've got a screencast of this as well, but I'll work through this here as well. So what's the formal charge on the S and the oxygens as well? And the average bond order for this sulfate ion for the best resonance structure based on formal charges. So we're actually going to see here, there's a number of possible resonance structures you could have. And we're going to look at the possible structures and see how they rank by formal charge. Okay, so let's start out with the total number of electrons. There's, zoom in. All right, so we've got, let's draw it. It's going to have a central sulfur. That's the least electronegative, surrounded by 4 oxygens. The total number of valence electrons, all of these have 6 valence electrons. But remember, it's a 2- ion. So we'll have 6 for the sulfur, 4 times 6, plus 2 more electrons for a total of 32 electrons. And the way we've written it, we start out by writing the bonds in between them. We've got 24 electrons left over to put in lone pairs. Well, 24 electrons to put in lone pairs, that's 12 lone pairs. So we can just probably start out just by completing the octet of all the oxygens by putting lone pairs there. And actually, you know, sulfur has a lone pair as well, right? Sulfur doesn't have a lone pair. Sulfur satisfies the octet rule already. So we could say, you know, that's a valid Lewis structure right there. But now let's look at the formal charges on it. So for the formal charges on the oxygens, they have the oxygen at 6 minus 6 lone pairs minus 1/2, 2 would be a -1. So each of these oxygens is -1. And then the sulfur is going to be 6 minus 1/2, 8 is going to be +2. +2 formal charges. +2 formal charges are bad. You'd say, you know, we should be able to have less charge separation than that. This is sort of saying all the electrons are out at the edge and the sulfur is feeling very lonely and unelectroned. So what could we do? Well, if we're willing to violate the octet rule, we can expand the octet, which we can because it's sulfur. Sulfur's down on the next row. It has access to we're filling in 4p electrons, so it has access to the 3d electrons. So let's bring one of these in. Let's make a double bond there. And then, oh, that is not a sulfur. That's an oxygen there. Oxygen, oxygen, oxygen. Okay, these are all lone pairs. Great. So these still have, no, they don't have, they do not have formal charge 0. They have formal charge -1. They haven't changed from the previous structure. But this oxygen now has a formal charge 6 minus 4 minus 1/2, 4. We've done this calculation a number of times. It has a formal charge of 0. And sulfur here now has a formal charge of 6 minus, well, now it's 1/2 of 10, which would be plus 1. We've made things a little better at the cost of expanding the octet, which is not a very high cost for something down on that row where we have access to the 3D electrons. We've lowered the total number of formal charges. But why not go further? Why not pull in another of the double bonds? In that case, we'd have oxygen with 2 double bonds, sulfur, double bonds here, and then oxygen, and now we draw that, and this is a 2 minus overall. Again, this is a 2 minus overall. And now what we notice is that we have a formal charge of -1 here, -1 here, 0 here, 0 here, and sulfur is 6 minus 1/2. It now has 6 bonds, but that would leave it with a formal charge of 0. So this is, by formal charges, the most stable structure of the sulfate ion. And this is the one that experimentally is the most consistent. What's the bond order here? There are going to be, which of the two ones are stable, really, which of the two are double bonds. Remember, it's an average of all of them. So really all of them, in the stable structure, we have two double bonds and 2 single bonds in all of these most stable structures. And so we'd say the bond order is approximately 1.5. Maybe it's a little lower than that, right? Because, there is some contribution for the other resonance structures. We can't really quantify it, but it'll be close to 1.5 because in all of the stable structures, they have 2 double bonds and 2 single bonds. So bond order of approximately 1.5, maybe it's 1.4, but these are sort of qualitative measures anyway. You'd have to do like the full quantum mechanics to know this. So in this case, we have both the lowest number and the lowest magnitude of formal charges. So that is the most stable biformal charges. That is the one that we expect to be the best description of the structure of the sulfonate ion.